Before I move on to the propagation part of the solver, I just want to mention that in MiniCP, we have a factory class that contains all the static methods that are useful to create the objects. And this is also a way to decouple the implementation from the usage of the object themselves, because since everything is an interface, it's quite easy to change, for instance, the implementation of the variable in your model by just adapting the factory method. I close the parenthesis and I move on to the propagation part. So the propagation has one specific goal, which is adding constraint and computing the fixed point. And this will orchestrate the whole process inside each node of the search tree. It's implemented inside the solver interface. So we have a solver, it's an interface. The solver has a state manager that is able to restore the state and on backtrack. And then you have the post constraint that we have used for modeling the n-queens problem. This is really what you use to add a new constraint to your model is the post. And you can also specify that you want to enforce immediately the fixed point or not, if you want to postpone the fixed point computation. You have two methods for optimization, which is maximizing or minimizing a variable. Then you have the schedule that will schedule the constraint to the fixed point. And this was this method that was called from the variables. You remember when we were adding a new constraint that needed to be scheduled, this was the one that we were using. There is the fixed point itself, and there is here a callback on fixed point computation that you can also use if you want to be notified when the fixed point starts. One specific implementation of the solver interface is called MiniCP. Okay, this is the only one that is proposed by default inside MiniCP. And the constraints that are used and that needs to be propagated inside the fixed point will be stored in this array, which is a queue. Really, it's really a Java queue of constraints. Then you have the constructor, you have the post method, and then you have the minimize and the maximize here. Okay. So what schedule will do is that this propagation queue that contains all the constraint that needs to be propagated, the schedule method will simply add to the propagation queue the new constraint that you want to schedule for propagation. Okay, so it will not be executed right away, it will be added to the propagation queue. And one of the possible optimization that you can do is prioritize a little bit differently the constraints according, for instance, to the time complexity that they have. But this is not what we do in MiniCP. In MiniCP, we just append it inside the propagation queue at the end of the queue. And you see that there is a small optimization there. Here, the small optimization that we do is that we do not schedule a constraint if it's already inside the propagation queue. And so if it is in the propagation queue, we set that the constraint is already scheduled so that we do not add it twice in case you wanted to schedule 2 times a same constraint. This will not happen. This is an optimization because it's not necessary to schedule twice a constraint inside the propagation queue. The propagate method is a private method inside the solver. We'll simply say that the constraint is not scheduled anymore. It has been removed from the propagation queue, and then it will call the propagate method of the constraint itself. And this is exactly the propagate method that we have implemented, for instance, in modulo or in the different constraint or this kind of stuff. Okay, so this is the propagate method of the constraint, and it will apply the filtering algorithm of the constraint if it is still active. You see that if the constraint is deactivated, it will not be propagated. This is where it is tested. The fixed point algorithm will process the queue as long as it is not empty. As long as it is not empty, it takes the next one, the one on top, it removes it from the propagation queue, and it will propagate this constraint, okay, until it is not empty. So this is why it's called fixed point. Until we do not reach a fixed point, which means that there is no constraint to propagate anymore, we continue and we propagate it. It's not clear when it will finish. We cannot predict that exactly because the propagate method, as a side effect, might modify the domain of some variables that themselves will add some constraint inside the propagation queue. Okay, and so the propagation queue, when you propagate one constraint, may grow, shrink, grow, shrink, and so on, until it becomes empty. But you know that it will eventually converge, and so in a finite number of steps, this should terminate, since the domain of the variables can only reduce. And another reason for which you can stop is that there is an inconsistency that is thrown. Inconsistency means that there is a domain wipeout, or if you prefer, the domain of one of the constraints of the variables becomes empty. If one of the domain becomes empty, there is no solution. You need to backtrack. And this will be detected as an inconsistency exception that will be thrown from the domains themselves. And so if you catch this inconsistency, you first need to remove all the constraints inside the propagation queue before you backtrack in an ancestor node. In the next video, I will discuss about the state management. State management is a very important topic, especially for backtracking, because if you don't have the state management system that allows you to restore the state on backtrack, then it's impossible to implement the depth first search easily.